Hey there, and welcome to This Explainer. We're about to dive deep into the fascinating world of computer architecture to figure out exactly how your device thinks so fast. If you've ever marveled at how your computer instantly opens apps or processes massive chunks of data without breaking a sweat, well, you're about to learn the hidden engineering secret that makes the whole shebang possible. So let's start with the question that gets right to the heart of modern computing. Why does your computer process things so quickly? You click a button and boom, it's there. No waiting. The answer isn't just about having some ultra-powerful processor, it's really about how that processor gets its information. Today, we're decoding a brilliant concept from computer science known as cache memory. Here is our roadmap for today. We'll quickly cover the memory speed problem, how cache actually works, its anatomy, mapping techniques, the hardware magic of CAM, and we'll wrap up with how engineers maximize performance. Let's jump in. Part 1, the memory speed problem, pitting the CPU against main memory. To really grasp the headache engineers were facing, think of your CPU, the brain of the computer, as a brilliant, lightning-fast worker. This worker can crunch numbers at mind-boggling speeds. But their main memory, the RAM, is like a massive filing cabinet located way down the hall. Sure, it holds absolutely everything the worker could ever need, but it takes forever to get up, walk all the way down the hall, grab a single piece of paper, and walk back. If our brilliant worker has to do that for every single task, their incredible processing speed is literally wasted on walking time. This quote hits the nail on the head. The engineering dilemma was simple but tough. We needed the ultra-fast access time of really expensive memory, but we also needed the massive storage size of the cheap, slow memory. We essentially wanted to have our cake and eat it too. Which brings us to part 2, how cache memory works, acting as a high-speed bridge. The solution engineers came up with is so elegant. They built cache memory right in between the CPU and the slow main memory. Think of the level 1 cache, or L1, as a tiny little desk sitting right in front of our worker. It is lightning fast, but it's small. Levels 2 and 3 provide slightly larger, but slightly slower, staging areas. Maybe L2 is a bookshelf next to the desk, and L3 is a small cabinet inside the office. It creates this perfect, graduated system of speed and storage size. Now, the only reason this desk system works in the real world is because of something called locality of reference. All this means is that if our worker needs one specific file from a folder, there is a massive chance they're going to need the other files in that exact same folder very soon. So instead of walking down the hall for one piece of paper, they just grab the entire folder and plop it on their desk. Moving on to part 3, the anatomy of cache. We need to talk about blocks, lines, and tags. Before we start organizing this hypothetical desk, let's learn the lingo. First up is the block. This is the absolute minimum unit of transfer between the cache and the main memory. Back to our office analogy, the block is that entire file folder the worker carries down the hall. Next, we've got the line. Once that folder gets to the ultra-fast cache desk, it gets placed into a very specific slot. That slot is called a line. It holds the data block itself, plus some necessary control information to keep things organized. And finally, the tag. You can think of the tag as the sticky note slapped onto the outside of the file folder. Because the cache desk only holds a tiny fraction of what's in the massive main memory, our worker needs to know instantly what data is sitting in that specific slot. That sticky note, tag, provides the exact identifying address. The logic mapping out what happens when the CPU actually asks for data is quite elegant. It's a real-time decision-making branching process that happens inside your device literally millions of times every single second. Let's step through it together. First, the CPU asks for a word of data. It checks the desk. If the data is sitting right there, boom, we call that a cache hit, and the worker uses it immediately, blazing fast. But if it's not there, we get a cache miss. The system then has to trudge all the way down the hall to the main memory, bring the whole block back, load it into a cache line, and then deliver the data. All right, part 4, direct versus associative mapping. How do we organize all this? When we bring a block back from the main memory cabinet, how does the CPU know exactly where to put it on the desk? Well, the simplest method is direct mapping. This is a highly rigid system. It dictates that a specific folder can only ever go into one exact predetermined slot on the desk, no exceptions. Now, direct mapping is super cheap and easy to build, but it has a pretty fatal flaw known as thrashing. Imagine our worker desperately needs two different folders, but the rigid rules say both folders belong in the exact same slot. They'd waste all day constantly swapping them back and forth. Associative mapping completely solves this by being flexible. With this setup, a folder can be tossed into literally any open line on the entire desk. This leads us perfectly into part 5, Content Addressable Memory, or CAM, the actual hardware magic. Wait, if a folder can go anywhere on the desk, how does the CPU find it quickly without manually checking every single slot one by one? Enter the secret sauce, Content Addressable Memory. Standard RAM just cannot handle this. CAM is a highly specialized, totally different kind of hardware where the memory cells themselves have built-in comparison circuitry.
Here's why CAM is an absolute game changer. Instead of giving an address and asking what data is here, the CPU simply shouts out the tag it's looking for. The CAM searches its entire memory all at once, in parallel. If it finds a match, it yells back the location. And get this, it does this entire search in a single clock cycle. Yes, it's made of static RAM, so it's bigger and way more expensive, but that instantaneous speed is exactly what makes flexible mapping possible. Finally, Part 6, Maximizing Cache Performance, Tweaking the System for Speed. To push these architectures to absolute peak performance, engineers really only have 3 dials they can turn. Number 1, reduce the hit time so the cache is faster to read. Number 2, reduce the miss rate, meaning the CPU finds what it needs on the desk more often. And number 3, reduce the miss penalty. That just means making that agonizing wait for the main memory slightly less painful when a miss inevitably happens. And engineers have some incredibly clever tricks to pull this off. For instance, they might widen the memory bus to transfer way more words simultaneously, which slashes that miss penalty time. Or they might use something called a victim cache. This is a tiny staging area that catches discarded data. It basically holds on to data that just got kicked off the main desk, just in case the worker suddenly realizes, wait, I still need that. It's a brilliant way to save a long trip down the hall. So what's the big takeaway here? The cache architecture we just unpacked is the hidden engine powering literally every smartphone, laptop, and server on Earth. But as high-performance computing tackles massive AI models and huge data sets requiring unprecedented amounts of data, we are pushing these systems to their absolute limits. Will we need entirely new memory hierarchies, or will clever optimizations continue to bridge the gap? That is the billion-dollar question computer architects are racing to answer today. Thanks so much for joining me for this explainer.